So this is a continuation of our first video, logistic regression using R. Here I consider more than one explanatory variables. So we see that status is a response variable, and from length to I and div, these are explanatory variable, and status is our response variable. So first here I discuss model building method. First I consider stepwise regression, then I discuss another method. Already I discussed stepwise in my theoretical lecture. So first I stored this data in a data. So I select this. Now we see that there are so many NA. So we need to remove this missing value. For this we use this comment, that is na dot omit within bracket data that is na dot omit within bracket data I paste it here. Then if you write data dot omit, then you see that NA is removed. Now for stepwise regression I use following code. First I use model.null. Here I consider only intercept term. That is GLM within bracket status curl 1, since I use intercept, and data is data dot omit, and family is a logit binomial family. Now we paste it here and run this portion. Next, for full model, here I consider all explanatory variable. I use this code MIGR INSECT plus diet plus these are the explanatory variables. So for full model I use all explanatory variables. Paste this and run this portion. For stepwise regression, I use this code .null comma scope equal to list upper equal to model dot full. Direction here I use both. If you want forward, then you replace both by forward, and if you use backward, then you replace both by backward. And here I use chi-square test. So I copy this portion and paste it here. If you run this portion, then you get this following output. Now you see step by step. First, when you have only intercept term, then you see that your AIC is 92.34, and if you look at this table, then you see that release has minimum p-value. So from this we enter release to the model. Then when you enter release to the model, then you see that your AIC is 60.13, which is significantly smaller than AIC of null model, that is 92.34. When release enter into the model, then you look at the remaining p-value of remaining explanatory variables, then you see that upland has minimum p-value. So now we enter the upland explanatory variable into the model, then you see that when upland entered the model, then AIC of new model is 54.04, which is significantly less than previous model, where we consider only release as the explanatory variable, and the AIC was 60.13. So if you enter upland, then you get, along with release, then you get 54.04 AIC. So this is quite significantly small than previous one. So this model is better than previous one. Now look at the remaining explanatory variables. When already released and upland entered into the model, then you see that MIGR has minimum p-value. So now MIGR, if you enter MIGR, if MIGR is entered into the model, then you see that AIC is significantly smaller than previous one. Here if you enter MIGR along with release and upland, then you see that your AIC is 49.63, which is significantly smaller than previous one when only release and upland is considered, that is 54.02. Hence this new model, when we use release, upland and MIGR as a explanatory variables, is better than previous one. Now look at the remaining explanatory variables. Then you see that mass has minimum p-value, and now mass entered into the model, then we see that our AIC, if we mass enter into the model, our AIC is 48.64, which is significantly less than previous model, that is 49.63, where release and upland MIGR are used. So this new model, where release, upland, MIGR mass is better than previous one. So proceeding in this way, we see that for the next step, MIGR has a minimum p-value. If you enter MIGR into the model, then you see that your AIC is 47.07, which is less than previous one. And proceeding in this way, then we get final model where upland, MIGR, mass, ID, IV, INS, ECT, wood are explanatory variables. So this is the process, and final AIC is 42.03, and it is quite satisfactory. So in this process, stepwise process, hope this is our best model. But I should mention one point, as linear regression, here also stepwise regression method does not give the best model. There is no guarantee this is the best model, but hope this should be a satisfactory one. So now I want summary statistics or summary of final model. So for this I use this code model.final. Here I consider these explanatory variables, and for summary output, summary within bracket model.final. This is the output. For analysis of variance for individual term, we need car package. So first we need to install this car package and then write library within bracket car ANOVA model.final type 2 test word test. If you want another test, you replace this word. So this is the ANOVA table for individual explanatory variables. Next, R square. This is a pseudo R square. I already discussed this in my theoretical lecture. First one is McFadden R square. This ratio of likelihoods I discussed this first one, McFadden R square. This is a ratio of likelihood and it suggests the level of improvement over the intercept model offered by the full model. A small ratio of log of the likelihood indicate that the full model is a far better fit than the intercept model. Next I discuss, at one point I mentioned that this is similar as our R square of linear regression model, that is 1 minus sum of square due to residual by sum of square due to total. So this portion is nothing but a same thing as sum of square due to total, and this portion is a sum of square due to residual, and this is 1 minus this. So this idea come from this R square equal to 1 minus sum of square due to residual by sum of square due to total. Next, McFadden's R square, adjusted R square. So here I McFadden adjusted R square. Here we see that this is equal to 1 minus log L hat M full minus K is number of explanatory variable, by log L hat M intercept, that is null model, and L hat is a estimated likelihood McFadden's are adjusted R square in OLS by penalizing a model for including too many predictors. And this is a mirrors. McFadden's adjusted mirrors the adjusted R square in OLS by penalizing a model for including too many predictors. If the predictors in the model are effective, then the penalty will be small relative to the added information of the predictors. However, if a model contains predictors that do not add sufficiently to the model, then the penalty becomes noticeable and the adjusted R square can decrease with the addition of a predictor, even if the R squared increases slightly. Note that negative McFadden adjusted R square are possible, so this value may be negative. Next is Cox-Snell R square. This is the formula where capital N is the total number of observation. So this ratio of the likelihoods reflects the improvement of the full model over the intercept model. The smaller the ratio, the greater the improvement. Note that Cox and Snell pseudo R square has maximum value is not 1, that is it should be less than 1, and the maximum value is 1 minus log L hat null model or M underscore intercept to the power 2 by capital N. Check this. That is maximum value is 1 minus log L hat M intercept to the power 2 by capital N, which is less than 1. So Nagelkerk, Craig and Ahler's R square remove this drawback. This is the formula, and here we observe that this value, the maximum value should be 1, that is it should be less than equal to 1. I use this quote here. our companion, this package is required. Then use this nickel cake model.final for pseudo r square. Copy this portion and I paste it here. Select this, and if you run this portion, then you get this output. If you have this package R companion, and if not, then you need to install it. I already discussed how to install package in my previous video. So these are the pseudo r square values of the pseudo r square. McFadden is 0.700473, Coxnail 0.63732, Nagel Craig 0.833284. Now for overall p-value for the model, we use this code. For this we need dplyr package. This is the code. I use this code. Paste it here. Next, I use this code for final model, for final data. For this we need dplyr, and here only you consider those explanatory variables which is selected in stepwise regression method. So this is This is a final data structure, and you see that here Na is present, so we need to remove this Na. So for this I already mentioned, for removing Na or missing observation, we use na.omit within bracket data.file final. This is the code. I select this portion and paste it here and run this. Then you see that Na is removed. Next, now define null model and compare to final model. For this I use this code. This is the code. Copy this portion and paste it here. If you run here, I mentioned that I use chi-square test. This is the output. Next, for plot of standardized residuals, I need this package. For standardized residual LM test, we need package LM test. Then use this function IRT test model.final. Then plot for standardized residual, I use this function. For standardized residual, I use our standard function. Run this portion. If you run this portion, then you see that this is the output. This is the graph for standardized residual, and this is a LR test, likelihood ratio test. For likelihood ratio test, we need package LM test. And this is the comparison between null model and final model. And for plot, this is the code, and this is a residual, standardized residual plot. Now simple plot for prediction values, we need LYR package. First we store data in data final, where we use only those explanatory variables which I got from stepwise regression, and then omit na or missing value from data using na dot omit. Then use this comment predict model dot final type response, and for plot I use this comment. So stepwise the details are as follows. First, use dplyr package, then select the portion of the data where the portion is, or column of the data subset. This is a subset. Actually, this is a subset. The first one is status response variable and upland MIGR mass INDIV insect wood. These are explanatory variable, and these are obtained from stepwise regression. So I only use these explanatory variables. So select this explanatory variable along with response. We need this comment select from where data and the columns, that is status, upland, MIGR, and so on. This is the code. And then we need to omit NA or missing value. So we need to use NA dot omit within bracket data, from where data dot final, and I store it data dot final. Then next step, need to predict. I use predict function, and the final model is model dot final and type is response. So I select this and paste it here, and run this portion. If you want to see this, just paste it here, and this is the predicted value. Now for plot, we use this code. Copy this and paste it here. If you run this portion, you see this actual response in y-axis and predicted probability of one response in x-axis. Now next point is check of over dispersion. This is very important point. I will discuss in detail in my next video, check for over dispersion. Here I discuss this portion very little. Just I give a overview of what is over dispersion, what happens if this thing is arise, and how to detect whether the data is suffer from over dispersion or not. Over dispersion is a situation where the residual deviance of the JLM is large relative to the residual degrees of freedom. These values are shown in the summary of the model. One guideline is that, this is a thumb rule, mind it, this is a thumb rule. One guideline is that if the ratio of residual deviance residual deviance to the residual degrees of freedom residual exceed 1.5 is a thumb rule, exceed 1.5, then the model is over dispersed. Again I repeat this portion. One guideline is that if the ratio of the residual deviance to the residual degrees of freedom exceeds 1.5, then the model is over dispersed. Over dispersion indicates that the model does not fit the data well. The explanatory variables may not well describe the dependent variable, or the model may not be specified correctly for this data. If there is over dispersion, one potential solution is to use Cauchy binomial family option in JLM. Again I repeat this thing, I will discuss this portion over dispersion in my next video, and Cauchy binomial family and Cauchy likelihood in detail in my next video. Please stay with us. Here since I want to explain multiple regression in logistic, more than one explanatory variables, logistic regression, more than one explanatory variable using R, and stepwise model building using R for logistic regression. For this purpose, automatically over dispersion come to the picture, missing value come to the picture. So that's why here I just mention this portion and how to detect this thing, whether the data suffer from over disperse or not. If this data is suffer from over disperse, the whole procedure, we cannot use this procedure. If the data is not suffer from over disperse, then I only use this procedure. So we need to check it fast whether the data suffer from over disperse or not. So thumb rule is residual deviance divided by degrees of freedom of residuals. If this ratio exceed 1.5, then your data suffer from over disperse, or your data is over dispersed, or your data is suffer from over dispersion. And if not, that means this ratio is less than equal to 1.5, then you use this procedure only. So first we need to check whether data is suffer from over disperse or not. So for this we use this code. Deviance by summary model.final dollar symbol degree of freedom of residual df dot residual. This is the code. Copy this portion and paste it here. If you run this thing, then you see that this ratio is 0.482417. So data is not over dispersed. So the procedure is okay, that is likelihood ratio is we can use likelihood test or etc. likelihood procedure. So all these things is correct since this data is not over dispersed. Now we discuss another alternative method of model building using this compare.glm function. First step is create data frame with just final term and no NA. This is the first step. For this we need dplyr library. The comment is I select these explanatory variables and then omit, and these explanatory variables come from your stepwise regression method, and then omit NA from data final and I store it data.final. Now copy this portion and run this portion. Next step is define models to compare. First model 1, this is a null model. Then model 2, this is the model considering only one explanatory variable, that is release. This is just follow the step of stepwise regression. Then in model 3, another explanatory variables entered, that is upland, which I already mentioned in stepwise regression in this video. Next model, model 4, that is MIGR GIR enter. In model 5, another explanatory variable mass is entered. And model 6, INDIV entered along with release upland MIGR mass INDIV. Model 7, insect entered. In model 8, upland MIGR mass indived insert entered. See that here release is not present. Release is not present here. So this is model 8 and model 9. Here upland MIG mass indived insect wood is extra additional explanatory variable which is not in model 8. So again I repeat this portion. In model 1 is a null model. Model 2 just enter release as the explanatory variable. Model 3, another explanatory variable entered, that is upland along with release. And in model 4, another explanatory variable entered, that is MIGR along with release and upland. In model 5, another explanatory variable entered along with release upland MIGR, that is mass. In model 6, release upland MIGR mass already taken from model 5 and adding another explanatory variable INDIV here. In model 7, see that release is same for model 6 and 7, upland is same for model 6 and 7, MIGR same, mass is same, INDVI same, and additional explanatory variable, that is insect, is entered. Next, in model 8, see that release is not present here. This is absent. Then upland is present in model 8, MIGR present in model 8, mass is present in model 8, INDIV is present in model 8, insect also present is model 8. So one thing is not one explanatory variable, that is release, is not present here. So this is release is not present here. And model 9, you see that Upland is present in model 8, MIGR is present in model 9, mass is present in model 9, INDIV present in model 9, insect present in model 9. So say all this same as model 8, but one additional explanatory variable added here, that is wood. So this, we want to compare this 9 model which I already obtained from step by step procedure of stepwise regression, step by step output of stepwise regression, and I want to compare this 9 model. So I copy this portion and paste it here. If you run this portion, then you get this output. And now I use this for comparing this 9 GLM models. I use this compare .glm function and use compare capital GLM function and within bracket I write all model 1, model 2, model 3, model 9. But one thing you should keep in mind, I write model dot 1, not model 1. If you write it model 1, then you write it here model 1. So mind it, you should not forget this dot. It is not mandatory, you can use also model 1 and then you write it here model 1 also, and so on. I copy this portion and paste it here. If you run this portion, and this is the output, see the output. When for first model, that is null model, here I use so many criteria, that is AIC, AICC, BIC, McFadden, Cox and Nell, Nagelcake, and p-value. And already I mentioned an alternative to or supplement to using a stepwise procedure is comparing models with fit statistics. My compare.glm function will display, see, if you use stepwise, then only AIC is display, and if you use this, then you can see this function along with AIC. So this function is AICC, BIC, and these are the pseudo R square, and this is a p-value. Since here I use chi-square test, already I mentioned. The model used should all be fitted to the same data, that is the one caution should be used if different variables in the data set enter missing value, then you need to, already I mentioned this thing, you need to remove this missing value. And if you do not have any preference on which fit statistics to use, I might recommend AICC. That means if you have a no choice or no recommendation about the criteria of model building, then in that case you use AICC, BIC if you had rather aim having fewer terms in the final model. A series of models can be compared with the standard ANOVA function. So before I discuss this thing, I want to see this output first. So see that from this is the ranking, you also get this thing. See that the first this is the null model where AIC is maximum. Then this is model 2. For model 2 only consider release. In that case your AIC is this, AICC is this, and BIC is this, and the best model is here. The best model is 2 model is best, that is model 7, that is model 7. That is model 7, where I use explanatory variables as release, upland, MIGR, mass, INDIV, insect. And another model has same rank, that is model number 9, where explanatory variables are upland, MIGR, mass, INDIV, insect, wood. So this is based on, and you see that for if you look at model 7 and model 9, then you see that your AIC is 46.42 for model 7 and 44.03 for model 9, 48.90 for AIC C for model 7 and 46.51 for model 9, and BIC is a 64.05 and 61.67 for model 9. So if you look at this value, then you see that this one and this one, these two values, that is Cox-Snell and Nagle-Craig pseudo R square, are these two values are smaller than these values, and p values is smaller. So but this thing is very insignificant. This improvement is very insignificant. That's why these two ranks are same. And if you take a close look, then you see that your model 9, where we consider explanatory variable upland, MIGR, mass, INDIV, insect, wood, this model 9 is best. So not only go to this rank things, you need to close look of this and find out the best one, because this is due to the cutoff criteria. For that reason model 7 and model 9 may be the same, take the same rank. That is the reason. So not only look the rank, you need to close look of all values of these AIC, ICC, BIC, McFadden, Cox and Snell, Nagle-Craig p values, and From these portions we get, or we can conclude that model 9 is a best one. So this is just an example. In that way you can compare. So if you take all possible, that is 2 to the power, suppose there are k explanatory variables, 2 to the power k possible subsets, and you take all this model, that is 2 to the power k models, in that way, and you get these statistics, and from this you can obtain this model, which model gives the better. But it is tedious already. That is 2 to the power, maybe k is a 8, that should be 2 to the power 8 is huge, or even if more than 8, maybe in that case is 10 or 12. It is not possible to consider all explanatory variables. So that's why we need a shortcut method, and stepwise gives us a satisfactory result in most of the cases. And we need all these criteria and take a close look to get a best model. Now use ANOVA to compare each model to the previous one, and here I use chi-square test. For this I use this function ANOVA within bracket model 1 to model 9. Copy this portion and paste it here. If you run this portion, you get the output, and the output this is the output. Here I mentioned that a series of models can be compared with the standard ANOVA function. So this is a quote: model should be nested within the previous model or the next model in the list. So if you look at this model 1 to 9, then you realize this thing, and models should be fit to the same data, that is data dot na, or our data is data dot final. When comparing multiple regression model, a p-value to include new term, this is a thumb rule, mind it, this is a thumb rule. First I mentioned step by step. Once again, a series of model can be compared with the standard ANOVA function using this function. Model should be nested within the previous model or next model in the list in the ANOVA function. this is the list model 1 to model 9 using same data. When comparing multiple regression model, p-value to include new term, this is a thumb rule, p-value to include new term is often relaxed is 0.10 or 0.15. So this is a thumb rule. It depends on experimenter. In general, we consider this. If p-value less than 0.1 or 0.15, then we enter new variable. In this example, the models chosen with a stepwise procedure are used. Already I mentioned this thing. Model 1, model 2, model 3, all are, these models are obtained from stepwise procedure. And note that while model 9 minimizes AIC, one thing I want to mention, it is very important, that is in model 9 you see that a closed loop, you need to close loop, you need to take a closed loop. In model 9 AIC is minimum, and if you see that BIC in model 8 is the smallest. So this is very interesting observation, because if you choose any one criteria, so your best model may not be a best model. So you need to take all this criteria and take the model, or choose the model which meet most of the criteria, that is the which meet most of optimum value of the most of the criteria. Optimum means comparing among the all 9 models here in this example. See that why I choose 9, model 9, because in model 9 AIC is minimum, AIC also minimum in model 9. It is not satisfied here. McFadden also minimum, also maximum here. Similarly, Cox-Snell also maximum here. Nagelcake also maximum here, and p-value also smallest here. So out of 1, 2, 3, 4, 5, 6, 7 criteria, 6 criteria, if you 6 criteria best, we get for model 9 we get best value for 6 criteria. So that is the reason I choose model 9 instead of other model. That is the reason. Another interesting observation, that is, if you look at the ANOVA result, then you see that model 8, look at model 8, and the p-value of model 8 is this. And model 7 p-value is this. So from ANOVA result suggest also, you see that yes, it is true, BIC is minimum, in model 8. So again you see this portion. Our thumb rule is we consider the model whose p-value is less than 0.10 or 0.15. So you look at the ANOVA table, then you see that model line p-value is 0.101686. This is satisfied. And also in model 9, AICC's McFadden, Coxnell, Nickel-Craig p-values, all these are meet optimum value among these 9. And this also satisfied. But see, here BIC is minimum for model 8, but what happened here? This p-value 0.587066, which is larger than 0.10, 0.15. So this ANOVA result suggests that model 8 is not significant improvement of model 7. These results give support for selecting any model. See, why I telling this thing? That is, you can select either model 7 or model 8 or model 9. Either you select model 9, model 8 or model why I telling this thing? You can select either model 9 or model 10 or model 9 or model 10 or model 7, because if you look at model 7, then you see that your p-value is 0.030970, and see that AIC is 46.42, which is not significantly larger than 440.3. Similarly, 48.90 of your AICCs, which is not significantly larger than 46.51. Similarly, BIC also we can conclude in that angle, and McFadden also not significantly improved in model 9. This is almost same 0.95912 or and 0.6055. Again, this one not significantly larger, 0.8178, not significantly larger than 0.7989. P-value is almost, both are same or not same, but thing is that almost both cases almost tending to almost 0. So for that reason we can select 7. We can select 7 or we can select 8, because in 8 your BIC is small, and in 9 almost all criteria including your p-value. One interesting thing I want to mention in model 7, because if you look at the ANOVA table in model 7, your p-value is small than model 8 and model 9. So this is another reason for selecting model 7. Not only that this value is almost close to the optimum value among these 9, the reason why I am thinking about model 7, the reason is model 7, if you look at this ANOVA table, you see that in model 7 your p-value is almost your p-value is smallest among model 7, 8 and 9. If you considering model 7, model 8 and model 9, then the p-value corresponding model 7 is smallest. So this is the reason why I am going to select 7. Not so from this portion I see that model 8 and model 9 is comparable, even if model 7 also comparable, because these are not the criteria. If you consider only this criteria, then in that case your model 9 is best. But this is, if you look at the model building, so you need to consider all criteria and take a model or models which satisfy almost all criteria or close to each other. So from this we see that model 7, 8 and 9 are almost same. Then you look at this ANOVA table, then you see that model 7 has smallest p-value among 8 and 9. So one recommendation is you can choose model 7. Another recommendation is, because of this value and your BIC is minimum in model 8, so another recommendation is you can select also model 8, and because of these values model 9 is best, because model 9 satisfied almost except one PIC meet all criteria or meet optimum value of all criteria if you look at all these 9 model, and also its p-values lies in the thumb rule, that is, if you select the new term, if p-value is less than 0.10 or 0.15, and then this p-value is 0.1016, which is lies between model 8 to 7. So for this reason I can suggest you can consider either model 7, model 8 or model 9. And I think if you need to recommend one model in that situation, you should recommend model 9. Thank you. Hope you enjoy this class. Please stay with us. I already mentioned in this class I will discuss over dispersion situation and missing data analysis in my next video. Till then, please stay with us. Thank you.